Hi and welcome to my channel JaberTime. This is my first video for Calculus 1 and I'm starting with Limits Part 1. I called it Limits Part 1 because there is a lot more than what you're gonna see in this video. So by Sunday next week I'm gonna upload another one. I'll call it Limits Part 2 and I'll move on. So within weeks from now Calculus 1 material will be uploaded to YouTube channel. As you can see right here, the way I do it, if this is your first time seeing my video, I write my notes ahead of time so I could save you some time from watching while I'm writing notes and moving on slides. I'm trying to save you some time with having everything colorful, ready to the point. Hopefully that will help, because if I write all these notes as I go, a 25 minutes video will be probably like twice as much, so it's going to be 50 minutes. So hopefully you like it, and if you do like it, consider subscribing because there is way more videos coming. I just started a few months ago and there is a lot that I could upload to YouTube videos. Hopefully you like it. This is kind of like my way of lecturing, instead of using a whiteboard or instead of using papers and a camera pointing to the papers. I think from what I hear from some comments here and there that this is a new thing or they do like it. So let's get started. Limits Part 1. Average velocity. So I have titles, as you could see, and I'm gonna describe it little by little. Instead of me writing, I'm just gonna bring them in one by one. The function s of t represents the position of an object at time t, moving along a line. Suppose that s at 1 equals 84 and s at 4 equals 144. So I have two inputs, we have two outputs. Find the average velocity of the object over the interval of time 1 to 4. In lower math we call it x and y, x1, y1, x2, y2, and you know how to find delta y over delta x, which we call slope. That's pretty much the same thing here. So average velocity is the slope. Let's move on. To explain more, I don't have a function here to graph it, so I graphed a generic one, and usually that's what we do, a nice curve in the first quadrant. I'm pointing to a point 184 and the other point for 144. You could see them on the x-axis and you could see them on the y-axis also. Alright? Next. Slope of the secant line. You see this line right here? This is called secant. It crosses the curve at two distinct points. The slope of the secant line is the change in s divided by the change in t. In lower math we call change in y over change in x. So the slope, which is m, of the secant, that's not secant, the slope of the secant, this graph right here, is s of t1, as this is t1, minus s of t0, as if this is t sub 0, over t1 minus t sub 0. Alright. So the average velocity is the change in position divided by the change in time. VAV as velocity average is s of t1, that's 144, minus s of t0, that's 84, over t1 minus t0, which is 4 minus 1. And that's what we have. I carried it to the right side right here, as you could see, to focus on the calculations. That's what I have, and simple calculations will give me 20. Now this is called average velocity. What about if we need the slope not at two distinct points, at one? It looks like it's higher. You see that? If I graph it here and touches this point only, it's gonna go higher slope, or a bigger angle with the positive x-axis, a greater angle I should say. So how do we do that? That's the limits concept, and that's pre-calculus, and that's how calculus started. So if we want it at a point, exact point, not average between two locations, we call it not average velocity, we call it instantaneous velocity at an instant. Consider the position function. Now we have a function s of t equals minus 4.9 t squared plus 30t plus 20. Complete the following table. You don't see it yet. Then make a conjecture about the value of the instantaneous velocity at t equals 2. Here's the table. So if you go all the way from 2 to 3, we know how to find the average velocity. We just plug in 2, plug in 3, and finish s of 3 minus s of 2 over 3 minus 2, and the rest is done. I'm skipping all those calculations, and I have 5.5. It's a wide range between 2 and 3. We're trying to get to 2 at 2. So if you look at the numbers right here, it's planned 2 and 2.5. So we went halfway. 2 and 2.1. We got too close to 2 now. That's even closer. 2 and 2.01. 1 out of 100. 2 and 2.001. We're trying to get too close to. It's kind of hard to graph a secant line between this point and this point by hand, but you could imagine it. That we are moving the secant, fixing the point at 2, and moving the secant from 3 to 2.5 to 2.21 and so on. So, doing the calculations right here, 2 to 2.5, I have 9.175. So it went from 5.5 all the way to 9.715. That's a big difference. Alright, now 9.91, not a big difference. We're getting close. And 10.351. Looks like it's increasing. You could see from the graph, this is a parabola upside down, and I'll show you the graph in just a minute to support those numbers. Look at the last one, 10.395, 10.351, 10.395. So what do you think is happening? What's happening is, it looks like the instantaneous velocity appears to be 10.4 or approximate to 10.4 at 2. We're getting close to 10.4, as you could see. You could go more, but you get the idea. This is a graph. Now, I graphed it on my calculator. This right here, it's upside down parabola, and it has a y-intercept of 20. This is 20 right there. And between 2 and 3, you could see the secant. That's 5.5. That's 5.5. And we are moving to the slope of the tangent. This is the tangent, the blue one. Close to, approximate to 10.4. Alright? Now, the instantaneous velocity at t equals 2 is the limit of the average velocities as t approaches to. The slope of the tangent line at 2, 60.4. You get this number if you plug in 2 in the equation right there. Is the limit of the slopes of the secant lines as t approaches 2. I can't graph all the secants right here, it's gonna be too busy right there, but you get the idea. Let's take an example just to see the concept of limits now, because this section is about limits, and the whole idea for it is finding average velocity and instantaneous velocity as one of the topics. Okay, here's a graph. Use the graph of f in the figure to find the following values, or state that they do not exist if a limit does not exist, explain why. We need it at the critical point that we are kind of focused now right here, which is 1. We don't need to worry too much about part A for now, for this chapter, but we have it, so let's go over it. F of 1, the value at 1, it's darkened right here for you, so we're gonna find it. The limit of f of x as x approaches 1 with negative sign to the right side of 1, that means from the left. So we are approaching 1 from the left. This one right here says the limit of f of x as x approaches 1 with positive sign to the right side. That means we are approaching 1 from the right. And this is our conclusion if there is a limit. Alright? So walking on this piece right here, as x moves from 0 to 0.1 to 0.2 to 0.5 to 0.9 to 0.92, you want to get to 1, but you can't step on 1, you're too close to 1, you're actually following this segment. Alright, so your value is gonna reach up to this one. Okay, your outputs. Here we go. F of 1. What's f of 1? It's 0, sorry. F of 1 is 0 because it's right there. As I said, it's darkened. Your output is clearly here. This is 1, 0. Now let's see if you approach 1 from the left. If you approach 1 from the left, you are up here. Okay, you're close to this open circle. So what's the value? All the way up to 1, so it's 1. How about if you approach 1 from the right? You're getting closer to this point right here, getting down, so your values will be closer to 0, to the x-axis. That's a 0. Now notice the limit of f of x as x approaches 1 from the left is 1. From the left you're going up. From the right side you're getting to 0. Those are completely different from each other. It has to be equal to say that the limit of f of x equals that certain amount. So we're gonna say does not exist, since the limit from the right and the limit from the left are not equal. As you could see, guys, if this is your first time watching a video for me, I do my best to write all the notes, do the graphs, and make the slideshow so I could go over it and save you some time. Because writing this as I go, it's gonna be at least twice or 3 times the time. Okay, let's move on. Definition of limits. What's the definition of limits? Suppose the function f is defined for all x near a except possibly at a. We don't have to worry about if it's defined at a or not. That's for continuity later on. For now, we're just approaching limits from right and from left. If f of x is arbitrarily close to L, so the outputs are close to a certain number, like in previous example it was close to 9.4, as close to L as we like, for all x sufficiently close but not equal to a. So if a is 2, we're getting close to 2, but we can't plug in 2. We write the following. The limit of f of x as x approaches a is equal to L. And say the limit of f of x as x approaches a equals to L. I just said it twice. One-sided limit. That's left and right. That's why we call it one-sided. Let's take a look at the left one. Right, actually, the right-sided limit. That's the first one. So suppose f is defined for all x near a with x's being greater than a. You are to the right of a. That's why it's called right. F of x is arbitrarily close to L for all x sufficiently close to a with x is greater than a. We write the following. Limit f of x as x approaches a from the right equals L. This is what this one is describing. You're approaching it from the right and you're approaching a certain limit as an answer The first table was the idea to see the concept right here. And say the limit of f of x as x approaches a from the right equals L. Let's go the other way around, which is left-sided limit. Pretty much it's the same concept, but we are to the left of a. So I'm not gonna read the whole thing, it's the same thing, except when you are approaching a from the left, your x's that you're using are less than that number a. And we write limit f of x as x approaches a from the left equals L. Alright? Now, assume f is defined for all x near a, except possibly at a. As I said, this is pretty much is for continuity later on. This is what we have. The limit of f of x equals L as x approaches a if and only if those two are agreeing on L. If the limit from the right approaching x approaching a is L, and the limit of f of x as x approaches a from the left is also equals to L, if these two are valid, we have them, we could conclude that the limit of f of x as x approaches a, without saying right and left, is L. Same thing, if somebody gives you that, that means the limit from the right and the limit from the left as x approaches a is L. Finding limits from a graph. Here's a graph. Okay, let's find the limits at different points that the graph is showing. F of 1. We're going to consider one right here to start with. You see this one right here? It's defined to be darkened right here, which is all the way up to 3. So f of 1 equals 3. Now let's try to approach one from the left. We're going to be going down this way. And approaching one from the right, we are going to go down this way. So let's see. F of 1 is right there. 3. Limit from the left. What do you think? The limit as x approaches 1 from the left. Do you guys see it? It's right there. Okay. It's 2. From the right, it's leveled to be the same, so it's gonna be also 2. That's from the right. If the limit from the left and the limit from the right is equal to L, same L, 2, 2, then we could say that the limit of f of x as x approaches 1 is 2. Let's take another number. Okay? We dealt with the 1. We're going to deal with 2, and we're going to deal with 3 as an example, just to practice finding limits from graphs. So let's take 3 now. 3. F of 3 is all the way up here. This point is for the 3, and it's not defined here. So it's going to be 2. Alright? Let's see what's next, left or right. Okay, from the left. As x approaches 3 from the left, you are actually belonging to this line segment. So that's going to take you all the way up here, which is 4. Let's go from the right. From the right, you are coming this way, so outputs will be getting down less and less and less closer to this level. So it's going to be 1. Limit from left, 4. Limit from right is 1. So the limit does not exist at 3. Okay? Hopefully that is clear. Let's move on. I'm going to take the 2 here just for the convenience and explain the concept of left and right also from another point of view. It doesn't have to be always jumping and points being taken out. F of 2. What's f of 2 is up here, which is 3. See this point right here? That belongs to us. So it's 3. Let's go from the left. Approaching 2 from the left, you are close to this point, right there. Still 3. Approaching it from the right. Approaching 2 from the right, you are pretty much right there. Close to 2. So it's going to be also 2, 3. From the left 3, from the right 3. So it's going to be also 3 as a limit. Alright, done. Let's take another example. Hopefully this is so clear. I'm trying to go fast a little bit to save you some time, guys, as you could see. But I have everything ready for you, so you could pause and go back and see it. Another graph. Look at this graph right here. We're going to take different points as we practice in the first example. F of 2. See this 2 right here? It's defined to be all the way up at this point, the darkened point, which is 3. From the left, you're going to be close to this open circle, which is 2. From the right, you're going to be on this line segment, getting close to this, which is leveled up to 3. Alright? Limit from left is 2, limit from right is 3. Well, you could see at 2 it's broken, it's different levels. So the limit at when x equals or approaches 2 does not exist. Let's take another point. This time we'll take 3. It's defined here. From the right you're going to be walking on this curve. From the left you're going to be getting close to this open circle. So at 3 it's defined to be 2. Approaching 3 from the left, you're going to be on this line segment, so the answer is 3. Going from the right, you're going to be on this curve, so you're going to be closer to this level, which is 2. Limit from left is 3, limit from right is 2, so the limit as x approaches 3 does not exist. Let's take another point. This time we will take 4. Here's 4. 4 is nicely connected from left and right, and it's defined there. It's not taken out somewhere else. So, you know, everything's going to be smooth and quick right here. F of 4 is 3. From the left, you are going this way. Still 3. From the right, you are coming this way. Still 3. So left 3, right 3. So at that level, without saying left and right, it's going to be also 3. Okay, we're good. Move on. Evaluating limits graphically and algebraically. Sometimes we could plug in the numbers and see it. So let me show you how. This is an example. It's called piecewise function. It has 2 pieces. One to the right of -1, which is leveled to be 3, which is a horizontal line. To the left of -1, including -1, it's defined to be a parabola. X squared plus 1 opens up, shifted up 1 unit. The concern is about -1. I want to support you by showing you the graph. It doesn't say graph it, or actually it does. Sometimes it doesn't, but I usually do it just to support my explanation algebraically and whatever we can do to support. Here's the graph. To the right of -1, it's flat horizontal at 3. It's taken out from here because I can't be equal to -1. When I'm equal to -1, it's solid, part of the parabola on the left side, less than or equal. Okay, that's called piecewise function. We are concerned about -1, and -1 value will be 2. From the left will be 2. From the right will be walking up here higher to 3. So the limit, as you could see, the graph does not exist. But when I say algebraically, what do I mean by this? Let's take a look. Here's f of -1. As I said, f of -1 is 2. And here's what I mean by algebraically. F of -1 because negative 1 does not belong to me here, it belongs to me here. If I want to use negative 1 exactly and plug it in, I can't use this piece. I'll have to use this piece. So I take negative 1 square, which is a positive 1, plus 1. By plugging in the numbers, I get 2. X squared plus 1, when x is less than or equal to negative 1, just plug it in, you get 2 algebraically. Alright. Approaching negative 1 from the left will be this right here, the parabola, because this is to the left of negative 1, and which is also 2, as I said graphically. And if you want to use the algebra steps, you plug in negative 1 right here. Negative 1 squared plus 1 equals 1 plus 1, which is 2. Let's go from the right side. The right side will be greater than negative 1, so I will use this 3, and that's pretty much it. As steps, I'm just referring to that, so I'll plug it in instead of saying graphing. So I will use that as a fact, which is 3. So what's the limit? I said earlier, right and left are different. Left is 2, right is 3, so the limit does not exist. Let's take another example. Sometimes, this is a quick example, we have direct substitution. I don't have to graph it, we don't have to worry too much about details, it's not a piecewise function. The limit of this function, which is cubic, as x approaches 1, there's nothing to worry about. As you could see, I don't have fractions, I don't have anything to worry about, so I'll just plug it in. Direct substitution or algebra steps. Just plug it in, you get 2. Let's take another example. Here we have a problem. Limit x squared minus 7x plus 12 over x minus 3. As x approaches 3, if you try to plug in the 3, you will get a form of 0 over 0, which is undefined. So we have to approach it differently. Here we go. You go and factor the top part, and now x minus 3 and x minus 3 cancels. Now you could do that on one condition, assuming that x does not equal to 3, because you are approaching 3, so you can't plug in 3. Approaching 3 like 3.001 and numbers like that. So my fraction simplifies to x minus 4. But you have to say that next to it, because if somebody does not see your steps and looks at x minus 4, he will think that this is your equation. No, my equation right here is different. If somebody does not write this and say, okay, you have a line with a slope of 1 with a y-intercept of -4, and what's the domain? You're gonna say all real numbers. But originally, the domain is not all real numbers. The domain is all real numbers except 3, because you can't use 3. So you have to state that right here. Alright? So, when you approach the -1, approach 3, if you plug in 3 now, I could plug in 3. 3 minus 4 is -1. To support, this does not say graph, but as I say, like I always try to graph to support my concept right here. Originally, I cannot use 3. It's out of my domain. This is my graph. It's x minus 4, slope of 1, y-intercept of -4, but when I go through the x value equals 3, I have to take it out of my graph. Okay? Let's take another example. This one is defined as piecewise function 2x plus 1 if x does not equal to 0 everywhere except 0. That's how it's defined. At 0, it's being plugged in to be leveled at 5. Here's a graph. Slope of 2, y-intercept of 1, y-intercept of 1, but at 0 I mean, x equals 0, supposed to be up here, but it's not defined. I have to redefine it or move it up to 5. You see the 5 is dark? So that's my graph. F of 0 is 5. That's defined here, and the graph shows it. The limit as x approaches 0 from the left, you're walking this way. The limit of fx as x approaches 0 from the right, you're walking this way. They're both getting to the level of 1, and that's the limit. Okay? If f of 0 is also 1, like this point is filled right there, that's called continuity. Left and right, and at that certain point, they're all agreeing to the same value 1. That's later on, which is called continuity. We're considered here to focus on limit from left and right, as you could see. Alright, what is the squeeze theorem? Assume that the function f and the function g and the function h satisfy the following. 1 all the time is less than or equal to the second one, and the second one is less than or equal to the third one. So we have three functions kind of like on top of each other all the way. For all values of x near a, this is our concern, so they could be somewhere else, not valid here, but that's what we have, except possibly at a. Now, limit f of x, this right here, the lower one, as x approaches a, and limit of this one right here, h of x, as x approaches a, they're both agreeing or getting close to L, and this lives between them. That's what they call the squeeze theorem. He is squeezed between them. He's not going to go anywhere else. If this one approaches L and this one else approaches L as a value, when x approaches a, where this is going to go? It's not going to go to 5L. It has to go to L also. Okay? It's right here. Let me support with a graph. That's the meaning. F of x, h of x, as x approaches a, they're both approaching the same output, which is L. And this lives in between, is not going to go anywhere else. It has to go through to also L. Okay? That's called the squeeze theorem. Sometimes they call it the sandwich theorem. Suppose that limit f of x equals, as x approaches to, equals limit h of x as x approaches to, we're trying to speak with numbers, the squeeze theorem back in the previous slide. They're both equals to L, which is 5. Find limit g of x as x approaches to the same a, such that given that g of x, when x is getting close to 2, always lives between f of x and h of x. So what do you think the limit is? Do you think it's going to be 5 or something else? It has to be 5. Okay? Okay. Let's move on. So far past half an hour as far as I could see, and as you could see with all my notes, I'm trying to not to make it 1 hour or 2 hours, but I still have a few slides to cover. Let's move on. This is a different one, as you could see. Completely different. Well, this is actually what they're taking you to the limit, the great concept of the limit, which is when you move the secant and make it a tangent. In calculus, we're going to use a different name than slope. We are going to call it first derivative. And this is one of the forms for the first derivative. See, calculus is mainly 2 parts: derivatives or differentiation, and the second part is integration, which is, you could look at it one way or another as an inverse mode of derivative. It has its own applications. We're going to get into that towards the end of the semester. Alright, so as I said, this is a great example, as a huge topic of derivatives, which comes from the limit concept, moving the secant to a tangent, making that difference between 5 and 6 to 5 and 5 plus h, which is a very tiny number. Graphing calculators, this h right here, which is 5 plus h, as like 5 and 5 point. Most of the calculators are programmed to have an h 0.0001. You could of course change it, but this is where how the calculator could find derivatives is actually this formula inside, with h being 0.0001. Okay, let's move on to the algebra steps. How do you do this? Well, I can't plug in h. At least here we have a problem. 0 in the denominator is not allowed, and this is not our topic to go over concepts like that, but you could leave me a comment below if you have any concerns why we can't divide by 0 or anything of that nature. I'll do my best to respond to you. Okay, now here's what I'm gonna do. On top I have two fractions. The common denominator is between 5 plus h and 5 is the product of 5 and 5 plus h. Here it's missing the 5, we multiply by 5 up and down. Here it's missing the 5 plus h, so I'm gonna multiply the numerator and the denominator by 5 plus h. You could see it here, I'm bringing different colors. Instead of me writing it, I'm just pointing to it and save you some time. Well, now it's ready. We'll make it one fraction on top, and we'll write the denominator, which is the common, which is 5 times 5 plus h, and on top it's going to be 5 minus this much. Here we go. Applying the distributive property and simplifying, the 5 will cancel, as you could see. Now clean it up without the 5's. We have the following. So you can't simplify all over the place. You have to go step by step. Now, this is called mixed fractions. The main fraction bar is the longer one. I'm pointing to it with this division symbol. To simplify without confusion, right here, I'm gonna change the main division to a multiplication, but on one condition: flip this right here, or we'll call it the reciprocal. This is what I mean. So this is the top part right there. Instead of divide by h, I'm going to say multiply by 1 over h, which is true. Okay, same thing like in math, when we say, like, instead of saying plus 7, you could say minus -7. All right, we're almost done. I usually try my best not to have lengthy videos. That's why I stopped after this example, and I called my video limits part 1, so I could move on to limits part 2. If needed, I'll go limits part 3 and move on. So just now, after I simplify, I divide by h, because h is not equal to 0. It's approaching 0, which means I could do this. See, when we slash it, it's a shortcut of saying I'm dividing top and bottom side by h. That's the meaning. Alright, I could do that because h is not equal to 0. It's approaching 0. 1 and -1. I'll need to write the 1 right here, but the -1 on top is going to be right there. Now I could plug in the h. All these ideas, I call them techniques, I call them skills, I call them practice. You need all these tools to master math and move on. See, without algebra, you can't do calculus, order of operations and simplifying fractions and things of that nature. So this is -1 over 25. You don't know exactly what's behind this problem, but later on we're going to explain more. Well, anyway, we are now at the end, and as I said, if this is your first time watching a video for me, which I just started recently, I would really appreciate everything that you stay till the end. So I'll say the following for you. Thank you for watching, and I hope that this video was helpful. Hit the like button if you do like it, subscribe, comment below, and I'll do my best to respond back to you. And if you like this video, hit that bell icon to be notified when I upload new ones. I'm planning to keep uploading math all the way. This is what I do for living, math. This class is Calculus 1. I started the first video, so I'm gonna cover Calculus 1. I teach Calculus 3 and Calculus 4 at Cal State Fullerton. So last semester I was doing Calculus 4. So eventually I'm gonna have pretty much all the math. Calculus 1, Calculus 2, 3, and 4, and some other topics as needed. Alright? So, thank you. It's called JaberTime. This is my nickname, and this is what I'm called at my school. So I'm using JaberTime instead of JaberMath, and thank you for everything. Thank you. I'll see you in the next video, hopefully by next Sunday, if not before. Thank you very much.